Okay, so let's try and unpack this AI thing
Ah.
because it really feels like it's everywhere now, right?
Mhm.
In well, all our digital tools
Yeah.
and understanding the basics, the structure behind it all, that feels pretty crucial now.
Mm.
Not just for tech people, but for, well, everyone using these tools.
Absolutely. It's key if you want to actually leverage them effectively rather than just, use them blindly.
Yeah. So today, we really want to cut through some of the jargon, get a clearer picture of concepts like artificial intelligence, machine learning, deep learning.
Large language models, generative AI, kind
Yeah.
of the whole landscape.
Exactly. The goal is really to see how they all connect, how they fit together, especially how they end up creating these pretty amazing tools we hear so much about, like ChatGPT or Google Bard, but, without needing a PhD to follow along.
hmm And it's actually, it's quite fascinating how just getting a handle on the basic hierarchy,
Yeah.
how that can really clarify what might seem like super complex, cutting-edge applications. Think of this deep dive as maybe providing a focused lens, helping you see the power and maybe the limits of each bit of AI you come across, turning buzzwords into something useful.
Right, a practical map. Okay, so let's start broad, really broad. Artificial intelligence, a lot of people, I think, hear AI and immediately picture, I don't know, sentient robots.
Yeah, that's the sci-fi version.
But the sources we looked at paint a different picture. AI isn't just one technology. It's an entire field of study, like physics or biology.
Exactly. That's the crucial starting point. It's the overarching discipline, the big tent. It's dedicated to this grand idea of creating systems that can do things normally requiring human intelligence.
Okay, that makes sense. A huge field. So where does everything else fit?
Well, there's a pretty clear hierarchy. So machine learning, ML, that's a major subfield within AI.
Not just another word for it.
Definitely not. If AI is the big goal, ML is a key method to get there. It focuses specifically on systems that learn from data. They're not explicitly programmed for every single task.
Okay, learning from data.
Then, going deeper, you have deep learning. That's a subset of machine learning.
Okay, so AI, machine learning, deep learning.
Precisely. And deep learning is special because it uses these complex structures called artificial neural networks, lots of layers.
We'll get into those, I assume.
We will.
Yeah.
But inside deep learning, you find different types, like discriminative and generative models. And this is also where large language models, LLMs, fit in.
Ah, okay. LLMs are under deep learning.
Mostly, yes. And here's the key connection for today. Those tools you mentioned, ChatGPT, Bard, the ones generating text or images, they often live right at the intersection of generative models and large language models. That's where a lot of the magic seems to happen right now.
That hierarchy helps a lot already. Okay, let's drill down into machine learning then. The workhorse, you called it. So it's about programs learning from data to build a model.
Yeah.
And then using that model to make predictions about new stuff it hasn't seen.
That's the core idea, yes. It finds patterns in the input data during training. Then it applies those learned patterns to new, unseen data to make an educated guess or a prediction.
Okay, give me an example. The source mentioned shoes.
Right, the Nike Adidas example is a good one. Imagine you feed an ML model tons of historical data about Nike shoes. Things like, features, colors, marketing spend, where they sold well, price points, all that stuff.
Okay.
The model learns the relationships between those features and actual sales performance. Then you could show it the specs for a completely new Adidas shoe, one it's never encountered. And based on the patterns it learned from Nike, it could predict with some degree of accuracy how well that Adidas shoe might sell.
Wow, okay, so it's generalizing from past examples.
Exactly, generalizing patterns.
Yeah.
And within ML, there are two main flavors you hear about a lot: supervised and unsupervised learning.
Right, what's the difference there?
The key difference is the data they're trained on. Supervised learning uses labeled data,
Labeled, meaning what?
meaning each piece of training data already has the correct answer attached to it, like a label or a tag. It's supervised because you're telling the model what the right output should be for each input example.
Okay, got it. Like flashcards for the AI.
Sort of, yeah. Think about that restaurant example. You have data on orders, the total bill amount, and the tip someone left. Crucially, each order is also labeled maybe pickup or delivery. That label is key.
Right.
A supervised model learns from all this labeled history. Then, for a new order, you tell it the bill amount, whether it's pickup or delivery, and it predicts the tip based on what it learned from those past labeled examples. It's learning a mapping. Input features lead to the specific output label.
Okay, that makes sense for prediction. But what if you don't have labels? What if it's just raw data?
Great question. That's exactly where unsupervised learning comes in. Here, you feed the model unlabeled data, just the raw inputs, no correct answers provided. The model's job isn't to predict a specific label, because there aren't any. Its job is to find hidden structure within the data itself. Find patterns, groupings, anomalies.
So it's like exploring the data.
Exactly. Think about that employee data example.
Right.
Just plotting years at the company versus income. No labels saying manager or intern or anything.
Just dots on a graph.
Right. An unsupervised model might look at that raw data and notice the points seem to clump together. Maybe one cluster represents people whose income rises sharply with tenure. Another cluster might show slower, more linear growth. The model identifies these clusters without being told what they represent.
So it finds groups naturally.
Yes. Then the company can look at those groups and maybe label them afterwards, like fast track or steady growth. And when a new employee joins, they can see which cluster their data point falls into.
I see. So it helps discover structure you didn't know was there.
Precisely. And the operational difference is really important. Supervised models constantly check their predictions against the known labels in the training data and try to get better to close the gap. Unsupervised models don't have that direct feedback loop against ground truth labels during training. They're just trying to find the best way to organize or represent the inherent structure of the data.
That does raise a question then. How do you know if an unsupervised model is doing a good job without those labels to check against?
That's a deeper topic involving various statistical metrics about cluster cohesion or dimensionality reduction quality. But yeah, validation is different than just checking accuracy against known answers.
Okay. Moving on then, up the hierarchy. Deep learning. You said this is machine learning, but using artificial neural networks? That sounds complicated.
It can be mathematically, but conceptually. The core idea is inspired very loosely by the structure of the human brain. Think of layers of interconnected nodes or neurons. Information flows through these layers.
Layers upon layers.
And the key idea is that the deeper the network, the more layers it has, the more complex and abstract the patterns it can learn from the data.
So more layers equals more power, basically.
Generally speaking, yes. Early layers might learn simple things like edges or colors in an image. Deeper layers combine those to recognize shapes, then objects, then maybe even whole scenes. It learns a hierarchy of features automatically.
Okay, I don't need to be a neuroscientist, but I get the layered idea.
Exactly. And this layered structure is what allows deep learning to do some really powerful things, like tackle problems traditional ML struggles with. And it enables approaches like semi-supervised learning.
Semi-supervised. So halfway between supervised and unsupervised.
Kind of, yeah. It's super useful when you have a little bit of labeled data, but a ton of unlabeled data. Labeling data is often expensive or time-consuming, right?
Sure, I can imagine.
So take bank fraud detection. A bank might only be able to afford to manually label, say, 5% of its transactions as fraudulent or not fraudulent.
Okay, small sample.
But they have mountains of unlabeled transaction data, the other 95%. With semi-supervised learning, a deep learning model first learns the basics of fraud from that small 5% labeled set. Then it uses that initial understanding to help it make sense of the massive 95% unlabeled set. It sort of propagates the labels or learns underlying structures relevant to fraud even from the unlabeled data.
Ah, so it leverages the unlabeled stuff too.
Exactly. It learns from both, allowing it to build a much more robust fraud detection model than if it only used the small labeled set. It's about making a little bit of expensive labeled data go a much longer way.
That sounds incredibly efficient for real-world problems.
It really is. It bridges the gap when fully labeling everything is just not feasible.
Okay, now in deep learning you mentioned two types, discriminative and generative.
Right. This is a key distinction.
Discriminative models. They sound like they discriminate, like they classify things.
That's a good way to put it. They learn the boundary between different categories of data. Their main job is to take an input and assign it a label.
Like the cat and dog pictures example.
Yeah, perfect example. You train it on pictures labeled cat and pictures labeled dog. It learns the differences, the features that discriminate between cats and dogs. Then you show it a new picture, maybe of a dog. Its job is to predict the correct label, dog. It classifies the input.
Okay. Draw a line, pick a side.
Pretty much. Now, generative models are doing something fundamentally different. They don't just learn the boundary between classes. They learn the underlying patterns of the data itself. They learn what makes a dog look like a dog or what makes text sound like human writing.
So they learn the essence of the data.
In a way, yes. They learn the probability distribution of the data, and because they understand that underlying structure so well, they can then generate completely new examples that look like they could have come from the original data set.
Ah, generative AI. Hence generative AI.
Exactly. So, back to the animal analogy. A generative model looks at thousands of unlabeled animal pictures. It learns common features, snouts, ears, fur, poses. Then, if you give it a prompt, like create a picture of a happy golden retriever, it doesn't just find an existing picture, it generates a brand new image of a dog that never existed, but looks realistic because it follows the patterns it learned.
That's the core of things like Midjourney or DALL-E, right?
Precisely, and there's a simple test you can use. If an AI's output is just a number like a probability score or a simple classification like spam, not spam,
Yeah.
it's probably not generative AI.
Okay.
But
okay.
if the output is something creative, natural language text, speech, a new image, music, code, if it's generating new samples that resemble the kind of data it was trained on, then you're likely dealing with generative AI.
That's a super helpful rule of thumb. Generate new stuff. Generative AI.
Broadly, yes. Though this raises interesting questions, How original is the generated output? How do we measure its quality or novelty? That's an ongoing area of research.
For sure. Okay, so generative AI isn't just one thing either. The source mentioned several types.
Oh yeah, it's exploding. Text-to-text is the most familiar, ChatGPT, Bard, generating articles, emails, code.
Right.
Then text-to-image, which we mentioned, Midjourney, DALL-E, Stable Diffusion. They make pictures from prompts and can even edit existing images now, too.
I've seen some incredible examples of that.
Then there's text-to-video, still newer, but models like Google's Imagen Video, Make a Video, they're starting to generate short video clips from text descriptions.
Wow. Video, too.
Text-to-3D is emerging. OpenAI's Shape-E can create 3D models, maybe for games or simulations.
Game assets from text.
And even text-to-task. This one's really practical, like telling your email app, summarize all my unread emails from the past week. An LLM, like Google Bard integrated with Gmail, can actually perform that action.
That's moving beyond just generating content to actually doing things based on language commands.
Exactly. It's about translating natural language into actions.
So where do large language models, LLMs, fit into all this generative stuff? Are they the same thing?
Good question. There's huge overlap, but they're not identical concepts. LLMs are a type of deep learning model, specifically focused on language. They can be generating text is a primary function, but not all generative AI models are LLMs, like image generators, and LLMs can also be used for non-generative tasks like classification or analysis.
Okay, related but distinct.
And a key concept with LLMs is this idea of pre-training and fine-tuning.
Right, you mentioned that earlier. What's the deal there?
So typically, these huge LLMs are first pre-trained on absolutely massive general data sets, like a huge chunk of the internet, books, articles, trillions of words.
Learning on everything, basically.
Almost. This gives them a broad understanding of language, grammar, facts, reasoning abilities. They become powerful generalists. Think of it like teaching a dog basic commands: sit, stay, come. A good foundation.
Okay, the pre-trained generalist.
But then comes fine-tuning. This is where you take that pre-trained generalist model and train it further on a much smaller, specific data set tailored to a particular task or industry.
Specializing it.
Exactly. So your generally well-behaved dog might get specialized training to become a guide dog or a police dog. It learns specific skills for a specific job.
I like that analogy. So how does that apply to LLMs?
Well, imagine a hospital. They could take a powerful pre-trained LLM from a big tech company. Then they can fine-tune it using their own internal anonymized medical data, patient records, research papers, diagnostic notes, maybe even X-ray reports.
Using their own specific knowledge.
Right. This fine-tuning makes the LLM much better at understanding medical terminology, interpreting medical reports, maybe even assisting with diagnoses based on the patterns in their specific data. It becomes a specialist medical AI.
So big companies build the foundation, and then others can adapt it.
Precisely. It creates this really efficient ecosystem. The huge cost of pre-training is borne by a few large players. Then organizations in healthcare, finance, retail, law, whatever, they can leverage that foundation and add their own domain expertise through fine-tuning without needing to build an LLM from scratch.
That makes cutting-edge AI much more accessible, doesn't it?
Absolutely. It democratizes it to a significant degree. You don't need billions of dollars to create a useful specialized AI anymore, provided a good base model exists. It really accelerates how AI can be applied across so many different areas.
That's quite a journey we've taken. from AI as this huge field, down through machine learning, the specific of supervised versus unsupervised,
Into deep learning with neural networks, semi-supervised learning,
distinguishing discriminative versus generative models.
and finally seeing how large language models are pre-trained and then fine-tuned for specific jobs.
Yeah. Understanding that whole structure, that hierarchy, it really does make the AI tools we use or hear about seem less like magic boxes,
It gives you a framework to place them in, to understand roughly how they work and maybe what they're good at and what they're not.
It definitely clarifies things. You see how these pieces build on each other.
Indeed. And this whole discussion, particularly around fine-tuning, it really highlights this trend towards AI becoming more specialized, more tailored, and also more accessible. It moves beyond just giant general models to potentially having highly capable AI fine-tuned for very specific niches.
So what's the takeaway thought there?
Well, it makes you wonder, doesn't it? If AI can be fine-tuned with specialized knowledge so effectively, what does that mean for the future of human expertise? And maybe more excitingly, how might these increasingly accessible, fine-tuned models create possibilities in industries or even parts of our personal lives that we haven't even really conceived of yet? What new capabilities get unlocked?
That is definitely something to chew on. How specialized can it get, and what does that enable?
Fantastic. Thank you for walking us through that. It really helped connect the dots. And thank you for joining us on this deep dive into the architecture of AI. Hopefully you feel a bit more equipped to navigate this evolving landscape.